Dear students, Assalamu alaikum. You know that in previous lectures we discussed about the definition of econometrics, theory of correlation, the simple linear regression model, which was followed by the multiple regression model. If you remember, we discussed the assumptions of the OLS. There were few assumptions, and at that time I also told you that if these assumptions are not fulfilled, then there will be issues in the estimation of the parameters. The result will not be reliable. There will be some complications for us in the derivation of the estimates of parameters, and in order to draw conclusion, in order to make policy decisions on the basis of those results. If the assumptions are violated, then we can face the numerous problems, like the problem of the heteroskedasticity. We can have the problem of multicollinearity, or we can face the other problem like the autocorrelation, etc. Our today's lecture is about the first econometric problem, heteroskedasticity. In our today's lecture, we will discuss what is the nature of heteroskedasticity. After discussion on the nature of the heteroskedasticity, we will discuss if the model is heteroskedastic, then what can be the possible consequences on the estimation, and how can we detect the heteroskedasticity, and further what can be remedial measures for solution of these problems. So before coming into the detail of the econometric problems, let me discuss the violation of the assumptions. Before discussing the violation, let's repeat the assumptions. Our first assumption was that UI is a random variable, its value is by chance. The second assumption was that the mean value of UI in any particular period is 0. The third assumption was the variance of UI remains constant in each period. The next assumption was UI has a normal distribution. The random terms of different observations UI, UJ are independent. The assumption number next was UI is independent of explanatory variables, and the explanatory variables are not perfectly linearly correlated. Similarly, explanatory variables are measured without error was another assumption, and numerical variables should be correctly aggregated, and the relationship being estimated is identified and correctly specified. These are few of the assumptions. You can give reading to the Kotsiani's book, Theory of Econometrics. This is a recommended book. Either you can also give reading to the Gujarati book. So my point of view was that in order to have reliable results, these assumptions should be fulfilled. But if these assumptions are violated, then we can have many econometric problems. But here we will discuss in our course 3 of those problems. Number 1 is the problem of heteroskedasticity. The second problem is the problem of multicollinearity. The third one, the problem of autocorrelation. So before going into the detail of the other problems, let's first discuss the problem of the heteroskedasticity. Students, if you remember one of the assumptions of the OLS, let me show you the assumption number 3. The variance of UI remains constant in each period. It is assumption of the OLS. One of the assumptions of OLS was that variance of each disturbance term UI conditional on the chosen values of explanatory variables is some constant number equal to sigma square. Or in simple words, the variance of error term remains constant in each period, which is assumption number 3 of the OLS. We assume that the model has constant variance. So if this assumption is fulfilled, we say the model is homoskedastic, and this assumption number 3 is called the assumption of the homoskedasticity. Homo means equal and skedasticity means spread. So equal spread or equal variance. Symbolically, we can say that the variance of the UI is equal to sigma square, which is a constant. Diagrammatically, we can show it as a summing function. We see that the variance remains constant even if the income increases, saving also increases, but the variance remains constant. If the variance of UI does not remain constant, it means that the assumption of the constant variance is violated, and we have the problem of heteroskedasticity. Traditionally, the assumption number 3 should be fulfilled, but if that assumption is not fulfilled, that assumption is violated, then we have the problem of heteroskedasticity. Symbolically, we see the variance of UI. This is not equal to sigma square. This is not equal to sigma square means the variance of UI is not a constant number. You see here the summing and income function. In the previous you have seen the equal spread, but here the spread of this. In these three cases, we see that the spread is not equal, the dispersion is not equal, and this means the variable variance. So, the case of the heteroskedasticity. We can also show it through another diagram. We see in this diagram that if we plot the values of the x and y on plane graph, we see that the dots are the combinations of the x and y. These lie near or on the regression line. This means that the spread is within a proper frame, within given limits. So it is the example of the homoskedasticity. While now students, if the variance is not constant, then we say that there is the problem of heteroskedasticity. We can see in this diagram that it is the regression line, and these are the scattered points of the x and y, and we see that with increase in the value of x and y, the spread increases. As the with increase in the values of x and y, the spread increases. The points, the dots, move away from the regression line. So this means increasing heteroskedasticity. In this diagram, part of the diagram on the graph, you see that with the increase in the values of x and y, we see that the spread is decreasing, and we are moving toward the regression line. This is the case of decreasing heteroskedasticity, while in the this diagram number 4, we see that initially the heteroskedasticity decreases, but then we see increase in the spread, so it is decreasing and increasing heteroskedasticity. We can discuss it with the help of example as well for the following the error learning model. As the people learn, their errors of behavior become smaller over time. Means as we learn more and more, the errors decreases. If we take the example of the language, as we have more and more practice, the errors in the language decreases. Similarly, in the typing error, we can say that as the typing practice increases, the error decreases, which means that in this case the variance is expected to decrease. Consider a figure, this figure, which relates to number of typing errors made in a given time period on a test to hours to the hours put in typing practice. As the number of hours of typing practice increases, the average number of the typing error as well as their variance decreases. and we see here that the typing errors and the hours of the typing, as we see that the typing error increases, we see a fall in the errors. Similarly, as income grow, the people have more discretionary income, hence more scope for choice about the disposition of their income. Hence, the variance is likely to increase with the income. Thus, in the regression of the saving in income, one is likely to find sigma square increasing with income because the people have more choices about their saving behavior. Similarly, companies with larger profits are generally expected to show greater variability in their dividend policies than companies with lower profit. Heteroskedasticity can also increase as a result of the presence of outliers. An outlying observation or outlier is an observation that is different from in relation to the observations in the sample. Sometimes we may have data. In the data we may see that after a few observation may be too small, or it may be too large. It is not like the others, not similar to other, which shows that there is some issue, an outlier. As the data collection techniques improve, we see that the errors decrease. Similarly, the heteroskedasticity can be due to the omitted variables as well. If a researcher omits a relevant variable from a regression model, the effect of this variable be captured by the error term. It will appear that there is a systematic relation between the disturbance and some exogenous variable, and the variance of the error term will not be constant across observations. Similarly, dear students, the problem can arise due to the non-linearities. The same problem occurs if researcher estimates a linear relation instead of a quadratic or any other nonlinear regression. We can have different forms of the model. It can be quadratic, it can be linear, or it can be exponential. So linear or non-linear n can be. So if wrong form of the model is used, the nonlinear model instead of linear, or linear instead of nonlinear, then we can face the problem of heteroskedasticity. Similarly, if a linear function is fitted to a regression or quadratic to an underlying quadratic or linear true model, or in a general a wrong functional form is chosen, then the term appear heteroskedastic. In simple words, if the wrong functional form is used, if you use logarithmic instead of the exponential form, or if the quadratic is used instead of logarithmic, then we can face the problem of the heteroskedasticity. Now, a question arises: if the model is heteroskedastic, then what is wrong with us? What will be the problems? What will be issues faced by a researcher if there is the heteroskedasticity in the model? Number one is we cannot apply the formula of the variances of coefficients to conduct tests of significance and construct the confidence interval. We see the formula of variance for B naught as equal to sigma square u into the sum of capital X square divided by n summation small x square. Similarly, the variance of B1 sigma square u 1 over summation small x n square. We use these formulas for to test the test of confidence, z-test and t-test. We construct the confidence interval with these formulas. But remember that when these formulas were developed, we assumed that the variance is constant. If this variance is not constant, means the assumption of constant variance is violated, then the test conducted, the confidence interval constructed will not be reliable. Similarly, the coefficients of estimates remain unbiased even if there is heteroskedasticity. Means that the effect of heteroskedasticity on the unbiasedness of the estimates will be zero. Mean it will not affect the unbiasedness of the parameters. The third is the least square estimate will be inefficient. They will not have no longer the minimum variance property. Dear students, we know that we call the least square estimators as blue. We call the least square estimates as blue. Best linear unbiased estimator. They are called blue because they are linear one, they are unbiased, and they are efficient. Means the least square parameters have minimum variance, due to which they are preferred over the other the estimates which are estimated through some other econometric methods. But if there is the problem of heteroskedasticity, then the least square estimates lose this property. Means in case of the heteroskedasticity, the minimum variance property of least square parameters is lost. Means, for example, we see, let this Bj hat and Bj bar are two variances, two parameters Bj. This Bj is the parameter which is constructed through the method of the estimated through the OLS, while the Bj bar is the estimate which is estimated through some other econometric technique. Traditionally, the variance of this parameter should be less than this. But if there is heteroskedasticity in the model, this will be greater than the variance of the estimate, which is calculated through some other econometric technique, which is the violation of the assumption. Similarly, the t-test and f-test based on OLS regression do not follow the f and t distribution respectively, hence the standard hypothesis tests are invalid. Now, question arises, these were few of the consequences of the heteroskedasticity. Now, question arises how one can find the heteroskedasticity. How as a researcher, how as an econometrician, I will come to know that the model is heteroskedastic. How can one know that there is the heteroskedasticity issue in the data? There are different methods to detect the heteroskedasticity, out of which the first method is the informal way or graphical method. In the informal way and in the two variable case, we can easily detect heteroskedasticity by simple inspection of the scatter plot. However, this cannot be done in a multiple regression line. In this case, useful information regarding the possible presence of heteroskedasticity can be given by plotting the square residual against the dependent variable or the explanatory variable. We can see it in this graph, that if we draw the residual on a graph and we see it, we see the variance is constant, then there is the homoskedasticity. Otherwise, down here in the graph, we can say this is homoskedastic, and we see increasing spread. It is show the presence of heteroskedasticity. So the first way to detect the heteroskedasticity is to plot it on the graph or graphical method. If you plot the observations on a graph, we can find the presence of the heteroskedasticity. We can have another test. We have a well-known test, Spearman rank correlation test, This type of the test can be applied to large and small samples. It is easy to conduct, not difficult. First, what we do that we regress y on x. This is the simple regression model. We obtain the after the estimates we obtain the residuals, EIs, which are the estimates of UIs. We give order to these errors, these UIs and XIs in ascending or descending order. Then we compute the rank correlation test. We discussed rank correlation in our lecture number 3, I think, in very detail. So compute this rank correlation, or Ex is equal to 1 minus 6 summation di square divided by n into n square minus 1, where d is the difference between the ranks of corresponding EIs and x. A higher rank correlation coefficient shows a presence of heteroskedasticity. If R in this case is higher, then we say that the problem is heteroskedastic. The third test to find the multicollinearity is the Goldfeld and Quant test. It can be used for large samples. The null hypothesis will be H0 UIs are homoskedastic, and it is tested against the alternative hypothesis that the UIs are heteroskedastic. The steps are very simple. We order the observations according to the magnitude of experimental variable x. Select some of the central number of observations, let's call it C, which we want to omit. We divide the remaining n minus C into two equal parts. Once again, first of all, we order the observation in ascending or descending order. Then we select some central number of observations which we want to omit and divide the remaining n minus C observations into two equal parts. We order the observation according to magnitude of the experimental variable x. Let's discuss in detail. We select some certain number of observations, let's say C, which we want to omit. We divide the remaining n minus C into two equal parts. So we have two subsample n minus C by 2 each. We fit a separate regression line to both the parts and obtain the sum of square of residues E1 square and E2 square. Then we calculate F statistic with this formula, summation E2 square by summation E1 square. If the F calculated is less than the F tabulated, then we accept H0 and conclude that the model is homoskedastic, otherwise it is heteroskedastic. Students, we can have some other tests as well, like the LM test, the Harvey-Goffrey LM test, and Park LM test. You can find I recommend you to study the Astidio and Stephen book for this purpose. And if you have any question, you can email me, you can contact me so far the heteroskedasticity is concerned. The material in this book, this lecture has been taken from Quant in 1973, the Gujarati book Basic Econometrics, and Astidio and Stephen Applied Econometrics by Palgrave Macmillan.